what is rate of flow? What is rate of flow or what is discharge? Right. Rate of flow or discharge means it is defined as the quantity of flowing fluid per second through a section of pipe or the channel. That means rate of flow or discharge means it is the quantity of fluid flowing through the pipe or quantity of fluid flowing through the channel per second is known as rate of flow or discharge. Right now, here two types. I told you compressible fluids, incompressible fluids. Incompressible fluids example liquids. Compressible fluids examples air. Compressible fluids examples air. Incompressible fluids, the units of rate of discharge or discharge is meter cube per second. That is flowing fluid per second. Whereas in case of compressible fluids or gases, right? Compressible fluids or gases, that the definition is weight of fluid flowing across the section. In case of gases or compressible fluids, rate of flow or discharge means weight of flowing fluid cross section per second is the rate of flow. The units of rate of flow in case of gases or compressible fluids is equal to kg force per second or Newton per second. Right, this is the standard formula. Rate of flow Q equal to or discharge Q equal to A into V. Q is the discharge, that is meter cube per second, and A is the cross sectional area if incompressible fluids or liquids. Q is the discharge meter cube per second, A is the cross sectional area, that is meter square, V is the velocity of flow, that is in meters per second. Next, continuity equation. Right, continuity equation. What is continuity equation? Continuity equation represents that the product of cross-sectional area and velocity at one point must be equal to the product of cross-sectional area and velocity at the another point. Right? Now, we are going to take one pipeline. This is section 1-1. This is section 2-2. The area at section 1 is A1, velocity at section 1 is V1. And area at section 2 is A2 and velocity at section 2 is V2. Right. What is the continuity equation? The product of cross-sectional area at one section A1 into velocity at section 1 V1 must be equal to the cross-sectional area at section 2, that is A2, and velocity at section 2 V2. Right? Must be equal. This is known as continuity equation. Or Q is equal to, already I derived. What is Q? Q is equal to A into V. Already I told you in the last class, last slide, discharge is equal to area into cross-sectional area. Therefore, Q is equal to A1 V1 is equal to A2 V2. This is the continuity equation. Right, Q is equal to A1 V1 is equal to A2 V2. Next, the product is equal to the volume of flow per second. This product is also equal to the volume of flow per second. In general form, the continuity equation is like this. Q is equal to AV, that is equal to constant, because suppose Q is equal to A1 V1 is equal to A2 V2 is equal to A3 V3. Like that, at three locations we are going to take in the pipe flow. This is the pipe flow. This is location 1, point 1, point 2, point 3. Point 3, the product of area into velocity here must be equal to product of area into velocity here and product of area into velocity at this point. If some cases area increases, velocity decreases. Velocity decreases, area increases. But the product of these two must be equal at one section to the another section. That is nothing but continuity equation. Right? Right. Continuity equation derivation. Continuity equation derivation. Right. Before going to derive the continuity equation, that we should follow, these are the steps. First one, what some assumptions we are going to take used in the derivation of continuity equation. Next one, we are going to consider one fluid element or fluid flow, and also taking the short time interval. Time interval we are going to take, and also consider the fluid flow within the short time interval. That is the second point. And third one, what is the distance covered by the fluid particle, and volume of the fluid particle, mass of the fluid particle, and mass flux. These points are involved in the derivation of the continuity equation. Right? Now we are going to discuss about one by one. Right. Assumptions in the continuity equation. Assumptions in the continuity equation. First assumption, that tube is having single entry and single exit. Right? Only single entry and a single exit. Tube should have only single entry and single exit. That is the assumption number 1. And 2, fluid is non-viscous. Fluid is non-viscous means that is the incompressible fluid. Fluid is non-viscous, that is the second assumption. And third assumption, fluid is incompressible. Incompressible fluid, that is also incompressible fluid means that is the ideal fluid. Right? One more assumption, that is the fluid is steady. Fluid is steady, fluid is incompressible, fluid is non-viscous. These are the assumptions we are going to take. Now we are going to derive the continuity equation. In the derivation of the continuity equation, right, these are the assumptions used. Right, next one, right, continuity equation. Right, continuity equation derivation. Here, consider the fluid flow for a short interval of time, that is known as dt. Consider a fluid flow for a short interval of time. Right? That means this is the delta x1. That means the fluid moving the distance delta x1 with a time of delta t, and the velocity at the lower end or at the inlet is v1, velocity v1, distance traveled is delta x1, the time is delta t. Right? Second point, right, the fluid will cover a distance of delta x1, and the velocity of the fluid v1 at the lower end. This is the velocity of the fluid. And one more point, at this time the distance covered by the fluid element, that we are going to determine. Here they have taken 3 points. One, we are going to take the time interval delta t. Within that delta t time interval, the fluid moving at a distance of delta x1. At that point the velocity of flow is v1. Right, now first we are going to determine the distance covered. What is the distance formula? Before distance, we know one standard formula, velocity is equal to distance by time. Here velocity is nothing but v1, that is equal to distance is nothing but delta x1 divided to time is nothing but delta t. v1 is equal to delta x1 divided by delta t. We want to determine distance covered. Therefore, delta x1 is equal to v1 into delta t. This is the distance covered by the fluid particle at a time delta t. Distance covered by the fluid particle at a time delta t. Right? Vx1 is equal to v1 into delta 1. Right? Here, all of you, please see the diagram here. This is the inlet or lower end. This is the outlet or upper end. At the upper end, same notations. This is the velocity at this upper end is V2, distance traveled is equal to delta x2, and cross-sectional area is equal to A2, whereas at the inlet or lower end cross-sectional area is A1. Right? Now, so at lower end we are going to take into consideration first, at lower end of the pipe, first we are going to determine volume, then mass of the fluid. Right? What is the formula for the volume? Volume is equal to area into distance traveled. Area into distance traveled. What is area? Area at the lower end is equal to A1 into what is the distance traveled? V1 into delta T. This is the volume of the flowing fluid at a time delta T at the lower end. Right? This is about volume. Volume is equal to A1 delta x1, that is equal to A1 V1 delta x1. Delta x1 is the distance traveled, delta x1 is also nothing but V1 into delta T. And another one, mass. What is the mass? Mass is equal to mass density of the fluid into volume. Mass of any item, mass of fluid, mass of solid or mass of any body, mass is equal to mass density of that item into volume. Right? Therefore, mass is equal to, now we are going to determine the mass of fluid in delta x region. Mass of fluid in the delta x region. Mass of fluid in the delta x region, that is denoted by delta m1. Right? Mass of fluid in the delta x1 region, that is denoted by delta m1, that is equal to mass is equal to, what is the formula? Density, mass density into volume. Mass density into volume. This is equal to mass density into what is the volume? Area into distance traveled. Area is A1. Say mass density is rho 1. Say here mass density at lower end is rho 1. Mass density at lower and upper end is rho 2. Mass density is rho 1 into cross-sectional area A1 into distance traveled is equal to what is V1 into delta T. This is the mass of fluid in the at the length of delta x1. Right? This is regarding at the lower end. This is the mass of fluid. Right? Mass of fluid is equal to rho 1 A1 V1. That means mass of fluid rho 1 is the mass density of the fluid at the lower end, and area into volume. Area is A1, volume is nothing but V1 into delta T. This is the mass of fluid at the lower end, right? That is the region of delta x1. Right? This is about mass of fluid at the lower end. Next one, mass flux. Mass flux. What is mass flux? Mass flux means is the ratio of mass per unit time. Mass per unit time. Therefore, mass flux is equal to mass per unit time. Right? What is mass? Already we have determined. Mass equal to mass density into area into volume is the mass density. This is the mass divided by unit time is delta T. Delta T gets cancelled. Therefore, mass flux is equal to rho 1 A1 V1. This is the formula for the mass flux. Right here, mass flux is equal to mass by delta time, mass per unit time, that is equal to rho 1 a1 v1 into delta t divided by delta t, delta t gets cancelled. This is equal to rho 1 a1 v1 is the mass flux at the lower end. Right, we have determined all the heads: volume, distance travelled, mass flux at the lower ends. Now we are going to determine the mass flux at the upper end. Right, now at the upper end we are going to determine the all the parameters. What is the distance travelled, what is the volume, what is the mass, what is the mass of the fluid in delta x region, and mass flux. Right, distance travelled is equal to what? Distance travelled equal to delta x2 is equal to, that is equal to v2 into delta t. Are you clear? Here velocity is equal to distance by time. Velocity is nothing but here v1, distance is nothing but delta x2 divided by delta t. Therefore delta x1 distance travelled is equal to v1 into delta t. Right? Distance travelled is equal to delta x2 is equal to v2 into delta t. Once distance travelled known to us, now we are going to determine the volume of the fluid at the upper strip, that is at a distance of delta x1. Volume is equal to, what is the formula? Area into distance travelled. Area into distance. What is the area? Area is A1. No. Area at the upper end is A2. Area is A2. And distance travelled is equal to V2 into delta T. This is the volume at the upper end. Okay. This is about volume. Right. Volume of the upper. This is over. Next one, mass density. Mass means same formula. Mass at the upper end or mass at the lower end, anywhere same formula. Mass equal to mass density into volume. Right, mass at upper end is equal to mass density into volume, that is equal to mass density at upper end is equal to rho 2. This is the rho 2 is the mass density at the upper end, and A2 into V2 into delta T. This is the mass of fluid within the region of delta x2 at the upper end is equal to rho 2 A2 V2 into delta T. Next one, mass flux. Mass flux is equal to, what is the formula? Mass flux is equal to mass per unit time. Mass per unit time. What is the mass? Mass is equal to rho 2 A2 and V2 delta T divided by unit time delta T. Delta T gets cancelled. Therefore, mass flux at upper end is equal to rho 2 A2 V2. Right. This is about mass flux at the upper end. Right. This is the mass flux at the upper end. Right here, rho is the density at the upper end, A is the cross-sectional area at the upper end, V2 is the velocity at the upper end. Right? This is about mass flux at upper end and lower end. Then next point, right here, one point you are going to remember, study. That means the density of fluid between the lower end of the pipe and upper end of the pipe remains constant with the time as the flow is steady. Therefore the mass flux at the lower end must be equal to the mass flux at the upper end. What is the mass flux at lower end? That is already derived rho 1 A1 V1. Right? This is the mass flux at lower end must be equal to the mass flux at upper end is equal to rho 2 A2 V2. Right? This is known as continuity equation. This is known as continuity equation, right? Mass flux at the lower end is equal to rho 1 A1 V1. Mass flux at upper end is equal to rho 2 A2 V2, right? This can be written as the standard form rho A V equal to constant. This is the continuity equation, right? This is the general continuity equation. This continuity equation is applicable, right? This is the continuity equation, right? Next point, right? This is already we have derived rho 1 A1 V1 is equal to rho 1 A1 V1 is equal to rho 2 A2 V2. This is also known as law of conservation of mass. Law of conservation of mass means the density, velocity, cross-sectional area at one section must be equal to density of the fluid, velocity of flow, and cross-sectional area at section 2. That is the law of conservation of mass, right? Now this is the standard formula. If the fluids are incompressible, what is happening? If the fluids are incompressible means rho 1 is equal to rho 2. The fluids are incompressible means the density of the fluid is same at point at section 1 and at section 2. Suppose this is one line, pipeline, this is section 1, this is section 2, this is section 2, this is section 1. The density is same at section 1 and section 2. Therefore, rho 1 is equal to rho 2. Oh, right? If in case of fluids are incompressible, this expression can be written as rho 1 A1 V1 is equal to rho 2 A2 V2. If rho 1 is equal to rho 2, therefore A1 V1 is equal to A2 V2. This is the formula in case of this is the continuity equation in case of fluids are incompressible. Right? And this equation can be written general form A1 V1 is equal to A2 V2 is equal to A3 V3. Then the general form is equal to A cross-sectional area into velocity is equal to constant. This is the continuity equation, right? AV is equal to constant, right? Okay. Are you clear? The continuity equation means A1 V1 is equal to A2 V2, that is equal to A3 V3. General form of continuity equation, AV is equal to constant. That means the cross-sectional area into velocity at one section must be equal to cross-sectional area into velocity at the another section, right? This is about continuity.